This webcast looks into a deeper dive of the understanding about what we observed in the sticky tape lab. The pieces of tape, the strip of foil, the paper, all those things that were used in this lab activity, in fact, everything in our universe is made up of atoms. Atoms are the basic building block of matter. They are the smallest particles which have all the features and properties of a particular element. These atoms are very tiny particles that move around in perpetual motion. They attract each other when they're just a small distance apart, but they repel each other strongly when they're squeezed together. So even though everything is made up of atoms, it's really impossible for humans to view a single atom. Atoms are approximately 10 to the negative 10th meters in radius, and the shortest wavelength in the visible light spectrum is 380 nanometers, or 3.8 times 10 to the negative 7th meters. That means it's impossible for the human eye to see a single atom. If you think of an apple, and if you could somehow magnify that apple to make it as large as the Earth, then the individual atoms in that apple would be approximately the size of the original apple. In this picture, we're looking at a drop of water on a leaf. And in this single drop of water, there are almost 850 quintillion, that means 18 zeros, of individual water molecules. Okay, so I'm going to show you a video that helps us see what an individual atom looks like.
Most fundamental scale, the atomic. One group from the University of California in Los Angeles have been getting up close and personal with nanoparticles of platinum, just a few nanometers across. Each of the tiny dots you can see here are actually individual platinum atoms, but researchers didn't stop at a two-dimensional picture. By imaging over 100 slices of the nanoparticle at different angles, then removing the noise with a special filter, they were able to map the location of almost every atom. The information was used to create a three-dimensional reconstruction of the whole particle in unprecedented detail. It may look blurry, but this particle is estimated to contain over 27,000 atoms, and so, like flies in a swarm, they appear to merge together. Every so often, though, we see the platinum's atomic structure align, granting us a moment of clarity.
Okay, so atoms are very tiny, but they are not the smallest particles that we know about. You can actually break an atom into subatomic particles. According to the modern standard model of an atom consists of subatomic particles called electrons, protons, and neutrons. There are really two parts of the atom: the nucleus, which is near the center, and the shells, where the electrons are continually moving. The nucleus, which consists of protons and neutrons, is the central part of the atom. Each proton has a positive electrical charge, but the neutrons are electrically neutral. So the nucleus as a whole has a positive charge. Almost the entire mass of the atom is contained within its nucleus. Electrons are much smaller than the protons and neutrons. They whiz around the nucleus in space in imaginary circular orbits known as shells. Each shell is associated with a fixed amount of energy, and each electron has a negative electric charge. Usually, an atom has the same number of protons and electrons, so the positives and negatives are equal, which means that the whole atom has no electrical charge. This illustration of a carbon atom is typical of how many textbooks will draw an atom. Different colors are used to distinguish the protons and neutrons and electrons. Concentric circles are drawn to depict the orbital paths of the electrons. This type of illustration is really useful for organizing our thoughts about the structure of an atom, but it is so unrealistic in many ways. So first, an atom is always in motion, and you would not be able to see the electrons because they are whizzing by so fast. Think of how the blades of a fan become blurred as they move around, and the electrons are really moving much faster than that. Second, the nucleus in this picture is just much too large for it to be a scale drawing. If a single atom could be magnified to take up about the volume of the room that you're currently in, the nucleus would be as small as a pencil point near the center. So on the scale of this drawing, the nucleus would be too small to be visible. This slide is showing a different type of illustration of an atom, and it also, of course, has some inaccuracy, but it tries to overcome the issues that I pointed out with the previous illustration. We cannot really identify the specific location of any electron at any particular moment, so we often describe the electrons as being in an electron cloud. That is the volume of space that the atoms are moving through all the time. Here, the gray shaded region represents the volume where electrons are moving. With the darker region near the center of the picture, that's where more electrons are located. The nucleus, depicted with the red protons and blue neutrons, is drawn much smaller. Although even in this picture, the nucleus is larger than it would be if the picture were drawn to an accurate scale. Okay, so going back to our pieces of tape for the sticky tape lab, each piece of tape is comprised of atoms, and the atoms have both positively and negatively charged subatomic particles. As a very simplistic way of representing the subatomic particles in the piece of tape, we're going to show plus and minus signs representing the charged subatomic particles that make up the tape. Notice how the positive and minus charges alternate and are evenly distributed throughout the piece of tape. This piece of tape is electrically neutral. That means that it has an equal number of protons and electrons. Throughout the tape, the charge is neutralized because a positive charge is always balanced by a negative charge next to it. So this slide depicts how we created charged pieces of tape. The top tape ended up with a positive charge. The bottom tape ended up with a negative charge. This is the figure that you should draw in step 20 of the lab report. So the pieces of tape were placed on top of each other on the table and were rubbed together. Then, when the tapes are pulled apart, some of the electrons from the top tape were pulled away and they stuck to the bottom tape. In this figure, the blue font represents the original subatomic particles on the pieces of tape, with an equal number of protons and electrons evenly distributed throughout the tape. The red font shows regions where there are excess charges, meaning places where there are an unequal number of protons and electrons. The top tape has lost some electrons because they were pulled off when the two tapes were separated. Now the top tape has an excess number of protons, and that means it has a net positive charge because it has more protons than electrons. The bottom tape has gained some electrons when the tapes were separated. So now the bottom tape has a net negative charge because it now has more electrons than it does protons. You have probably heard before that opposite charges attract and like charges repel. Objects that have the opposite type of electric charge attract each other. So a negatively charged bottom tape will attract a positively charged top tape. Objects that have the same type of electric charge repel each other. So two negatively charged bottom tapes repel each other. Also, two positively charged T-tapes repel each other. This type of electrostatic force is an action at a distance type of force. The two charged objects never need to touch in order to exert a force on each other. But in the sticky tape lab, we clearly observed that a charged object can also attract an electrically neutral object. In step 21 of the lab report, we're going to make a model that explains why the electrically neutral strip of paper was attracted to both the positively charged top tape and the negatively charged bottom tape. Paper is a type of material called an insulator. An insulator is a material in which atoms hold onto their electrons very tightly, so that the electrons are not able to be pulled away from their original atoms. This property of insulators is one reason that they are very poor conductors of either electricity or heat. Some common insulators include paper, wood, plastic, glass, porcelain, and styrofoam. In the atoms of an insulating material, the electron cloud can shift, but the electrons are not mobile. Because the electrons must remain with their original atom, we use circles to depict the atoms within the material. A plus sign near the middle of the circle represents the positively charged protons in the nucleus. The circle itself represents the electron clouds, where the negatively charged electrons are zooming around. The electron cloud can shift a bit from one side to another, but the negatively charged electrons must remain with the atom. And if the object is a solid, such as the strip of paper, the atoms are rigidly bonded to each other, so the atoms cannot move around the piece of paper. So first, we're going to explain how the positively charged T-tape can attract this neutral piece of paper. In this very simple depiction, the piece of paper is shown with 5 huge atoms. When the paper is brought near the charged T-tape, the negatively charged electron clouds in the paper are attracted to the T-tape's positive charge, right? Because opposite charges attract. The way we show this in our figure is to draw the plus signs on the right-hand side of the circles, which indicates that the electron cloud has shifted to the left. Now, to be clear, the nucleus did not really shift. It was the electron cloud that becomes slightly distorted, but this is the easiest way to draw what is happening. We say that the paper becomes weakly polarized when the electron clouds shift closer to the top tape. The side of the paper facing the tape now seems to have a more negative charge, and so the electrostatic force pulls the paper toward the top tape, right, because the opposite charges are attracting each other. The paper is still electrically neutral because it has an equal number of positive and negative charges. If you pulled the paper further away from the top tape, the electron clouds would return to being centered around the nuclei, and there would be no apparent charge. So there's an important word that we've introduced here called polarization. Polarization is a relative shift of positive and negative electric charges that is induced by proximity to a charged object. Let's also look at the situation where a negatively charged B-tape could attract that neutral piece of paper. Okay, so again, paper is an insulating material, and so we're representing the paper by drawing circles to represent 5 huge atoms on that piece of paper. When the paper is brought close to the negatively charged B-tape, its electron clouds are repelled from the B-tape's negative charge, because like charges repel. And so we're going to show that by drawing the plus signs being closer to the bottom tape. Because that is our way of drawing it to indicate that the electron cloud has shifted to the right. The paper becomes weakly polarized when the electron clouds shift away from the bottom tape. The side of the paper that's now closest to the tape seems to have a more positive charge now, and so the electrostatic force pulls the paper toward the B-tape. The paper is still electrically neutral because it has an equal number of positive and negative charges. If we could pull that paper further away from the bottom tape so that it's not close to any charged object, the electron clouds would return to being centered around the nuclei, and there would be no apparent charge. Let's repeat a little bit of the information about how a charged object can attract a neutral object that's an insulator, like the piece of paper. Polarization is a relative shift of positive and negative electric charge induced by proximity to a charged object. Insulating materials like paper can only become weakly polarized because their electron clouds are very limited in how far they can move. The cloud can shift, but the electrons cannot leave the atom. When we are showing insulating materials like paper, we draw large circles that represent the atoms, and the circle represents the electron cloud. We draw a plus sign inside the circle to represent the nucleus. Okay. In step 22 of the lab report, we're going to make a model that explains how the electrically neutral strip of foil could be attracted to both the positively charged T-tape and the negatively charged bottom tape. So foil is a material called a conductor. A conductor is a material in which the electrons in the outer shells, those are the valence shells, are free to migrate throughout the object. Metals like foil, aluminum, copper, and so on are all good conductors. When we are drawing a figure to show a conducting material, we do not use circles to represent the atoms. And that's because the electrons are free to move outside the atoms. They're not constrained inside that circle anymore. They can literally move from one end of the piece of foil to the other end of the piece of foil. So here, the plus signs represent the evenly distributed nuclei of the atoms in the foil. And notice that the nuclei are evenly distributed throughout the foil because the nuclei do not move, because the atoms are rigidly bonded to each other. But the free electrons are able to move, and their negative charge is very attracted to the positive charge of the T-tape. And so we see electrons gathering as close as they can get to the positively charged T-tape because opposite charges attract. Notice in my picture I've shown 6 plus signs that represent 6 nuclei, and so I'm only showing 6 free electrons, because overall this piece of foil is electrically neutral. It has an equal number of positive and negative charges. If we were able to take the foil further away from the T-tape, those electrons would return to being evenly distributed throughout the foil. So this is polarization as well, but here the foil, which is a conducting material, becomes strongly polarized. One end of that piece of foil, the end that's closest to the T-tape, it really does have an excess of electrons at this point. They've all gathered down there, and the other end has a deficit of electrons because they all migrated to the other end. So we see a much stronger difference in charge from one end of the foil to the other. The other situation is how a negatively charged bottom tape can attract this neutral piece of foil. So now the free electrons in the foil are repelled by the negative charge of the bottom tape. And so they migrate as far away from the bottom tape as they can get. And so they're going to the upper right-hand corner here of this piece of foil. So because of that, the side of the foil that is closest to the bottom tape now appears to have a positive charge. It has lost so many electrons to the other, who moved to the other end, and so the positive charged side of the foil is attracted to the negatively charged B tape, and they pull closer together. Now the foil is still electrically neutral, and if we pulled it away, those electrons would return to being evenly distributed throughout the foil. Okay, so just repeating a few of the important points here. Conducting materials like foil and other metals can become strongly polarized because the free electrons can migrate through the entire object to one end or the other. They are not constrained to staying inside their atoms. So since they are not constrained to stay inside the atom, we do not draw circles when we are representing the microscopic particles in conducting materials. We just draw plus signs to represent the nuclei and negative signs to represent those freely mobile electrons. So I just want to pull this information together to summarize what you might see when you bring two objects together. If you bring two objects close together and there is no interaction, that tells you that both objects must be electrically neutral. I'm going to the far right side of the table. If you see that the two objects repel, then they must have the same charge, because that's the only explanation for two objects repelling, is that they have the same type of electric charge. But if you see the two objects attracting each other, then there are two possible reasons. One scenario is that both objects may have an electric charge, but their charges are different. So one is negatively charged and the other is positively charged. But another scenario that would explain why the two objects attract is that one object is charged while the other object is neutral, and it is becoming polarized by being close to the charged object. So if you are trying to determine the type of charge on an object, the clearest test is to find out whether it is repelled by an object that you know it has either a positive or a negative charge, because the only reason that an object is repelled is because it has the same type of charge as the object that's being brought close to it.